This video is going to be all about relative velocity and in particular we're going to look at what happens when you're crossing rivers. Now it doesn't have to be a river. This applies to any kind of movement in water that's moving. The river is an easy one to visualize, so we'll do a river. Okay, so what I'm going to do is just draw a picture and kind of set it up. And then we'll talk about what happens. Now some of this we've already talked about a little bit, so this will seem familiar. If I draw a river here, something like that, and just for the sake of argument, we'll say that the river happens to be about 100 meters across. And let's say that here you are on your little boat at one side of the river, and there's a spot over here, we'll call it little spot X, where you're trying to get to. And so your goal is to paddle to that spot. But there's also a current in the river. So I'm going to put the current, for now I'll just put it over here, sideways, BC current. Okay? And you are going to paddle in such a way that you aim directly for the spot that you're going to. So this vector will represent VP, your paddling speed. Okay? And I'm going to tell you that your paddling speed is going to be, let's say, 4 meters per second. But your speed of the current, we're going to say, is 2 meters per second. Okay? So now we just want to explore what will happen. Well, what will happen will be the result of two things. Okay? I'm going to write this in red. Your motion will be the result, right? And I guess when I say motion, I mean your actual velocity, the way you'll actually move. Whoops, I said that. Okay, the way you actually move is what I mean by your motion. And it will be measured relative to the shore. Okay, relative to the shore. So it's like as if someone were watching you from shore. The result would be what they would see, how your boat would move through the water. Your motion will be the result. Ooh, I can't spell today at all. The result of two things. The paddling velocity, which is the velocity of your boat as it moves through the water, and the velocity of the current, or the current velocity, because the current will be drifting you as you move. Now we can say that in a mathematical way. What we can say is, instead of all those red words, we can say that the resultant velocity, the word resultant just means the result, will be equal to the velocity of your paddling plus the velocity of the current. But we have to remember that these are velocity vectors. And so it would be easy to think that you could just add up 4 and 2 and say the answer is 6, but that's not true because of the direction part. So when we want to add these vectors together, we have to do it using the vector addition method, tip to tail, like we learned the other day. So we can't just add 4 and 2, we have to draw an actual triangle, which I'll draw over here on the side. So we had a paddling velocity which was going straight across the river, and then if we go back and look at the velocity of the current, this blue arrow, I want to pick that up and I want to bring it over so that it's tip to tail with the paddle velocity. So I'll just pick it up and draw it over here, paddle velocity. So current velocity. And then the black one is the paddling velocity. Now, because those vectors are tip to tail, right here you can see they're tip to tail, and that's the way we add them, and that represents VP plus VC. And the answer is the resultant, which would be the vector from the start to the very finish. So this triangle is actually another way of saying this mathematical statement. They mean the same thing. And we often use a vector triangle instead of a statement like this or along with it to solve a problem that we might have. The other interesting thing to note in this particular triangle is you're paddling directly perpendicular to the current. So that's a 90-degree triangle. That'll help when we start doing the math. So let's ask ourselves a couple of questions then. Question number one that we're going to ask ourselves is, how long will it take you to cross the river? How much time will it take? How long will it take to cross the river? Now, in order to solve these problems, what we're going to do is we're going to do a very convenient thing. We go back to our original picture. Okay. What I can do here is I can draw on top of this the same triangle that we had before, so we can see it. It's the same one. What we're saying is that the resultant velocity, the way that our boat will move through the water when viewed from shore, is a combination of the paddling velocity along with the current. This is kind of like, as we said yesterday, looking at the 7 fruit, or looking at it as 3 apples and 4 bananas. The red arrow is the 7 fruit overall. But you could ignore the red arrow completely, and you could look at the very same thing as the black arrow plus the blue arrow. But you would never look at them all together at once. You either look at the red arrow or the black and the blue arrow. Because the red arrow is 7 fruit, and the black and blue arrow is 3 apples, 4 bananas. But you can't look at them all together, or you'll end up with too much fruit. Right? So here, what we're going to do is notice that the black and the blue arrow are at 90 degrees, and they represent the vertical and horizontal components of this red arrow, don't they? They actually represent how much of the red arrow is uppy-downy and how much is lefty-righty. And so we're going to use that fact. The other thing you must remember is that uppy-downy has no effect on lefty-righty. Horizontal motion has no effect on vertical motion, and vice versa. If you turn an Etch-a-Sketch knob sideways all day long, you will never get it to go up and down. Has no effect. And if you turn the up and down knob, you'll never get it to go left and right. It has no effect. Which means we can take this and we can split it apart and look at the up and down and the left and right completely separately, because they have no effect on each other. So we can treat each dimension, up and down or left and right, as a separate thing altogether. So that's kind of what we're going to do in solving these problems down here. How long will it take to cross the river? Well, crossing the river involves looking at this direction, getting across the river, right, from one riverbank to the other. And so if we look at our picture just above there, we can see that there's only one arrow that's pointing along that direction, and it's this. It's the paddle velocity. So that's the vector that we're going to choose to determine how fast we're going to move in that direction. The velocity we pick is the paddle velocity, which was given to us back here as 4 meters per second. So we'll use that as our velocity for crossing the river. We also know that the distance across the river is 100 meters. And because we're now talking about distance in 2 dimensions, we're going to put a little y beside this one to remind us that that's the uppy-downy distance we're talking about. I say uppy-downy, I know that the river is not really high or low, but on the board it looks like up and down. So it's the vertical dimension, right, across the river. And then we're looking for time. And because it's a constant speed motion, we can do a nice easy d equals vt, and it's vp that I'm using. So there's my equation, 100 meters, and it's 4 meters per second times t, so I'm thinking that the time here would be 25 seconds to cross this river. Yes? Well, not the time to cross the river. The question is, would the time be affected by the current? It depends how you look at it. So let's look at this again. If we just look at the red arrow and ignore the black and the blue arrow, then we would have to figure out how much time it took you to follow that red line and get to the other side, and we have to know how far that was, and we have none of that information. The 100 that we have was across the river, straight across. So by looking only at the black and blue arrows and ignoring the red arrow, what we've said is that if you just look at the vertical motion, it'll take you 25 seconds to get across the river. But there is an important difference. Where across the river, right? This doesn't mean that we're going to end up exactly across from where we started. All it means is we will leave one riverbank and we'll hit the other riverbank 25 seconds later, but we didn't consider any sideways motion, so we don't know whether we'll land right here, or go this way, or go that way, or anywhere. All we said is 25 seconds to start at one riverbank and get to the other. And that's because we haven't yet considered any horizontal motion, which of course is what we'll do next. That would be, the question we'll ask for that is, question number 2, how far will you drift while you're aiming your boat straight across the river? Okay? And again, we talked about this before, so it shouldn't be too bad. If you do try to aim straight across the river and follow the black line is where you're pointing your boat. The current is going to push you a little bit to the right. And the red line is the actual path your boat would actually take if you were watching from the shore. So, let's go and figure out how far we will drift. We're now talking about motion going this way, back and forth, or the x direction motion. This was the y up here. So let's see what we have on our picture. Which arrow is an x arrow? Looks to me like the blue current velocity. So that is the velocity we'll use to determine what's happening sideways. So the velocity we want is now the current velocity, and it was 2 meters per second. And we don't know how far we're going to drift. I'll call this little d dx. See the difference? This is the sideways distance. But we don't know what that is, so I'll put a question mark. The other thing we need is, of course, is the time. And now we see, oh, I don't know that either. Or do I? Let's think about this. If I'm in a river and I'm paddling for 25 seconds, because that's what it told me would be the time across, once I'm across, I get out of my boat, I'm not drifting anymore. So the time for the vertical motion must be the same for the time sideways. Right? This is the time in the water. That's how long you're in the water for. So that's how much time the current has to drift. So I can borrow that and use it here. Because remember, when we look at the black and the blue arrow, we have to remember that they're both happening at the same time. So the time is the same for each. So I'm going to borrow 25 seconds here, so I do know what that is. We'll erase that. And let's do 25 seconds. Now we can do another d equals vt. This time I'm looking for the horizontal distance or displacement, and I'm going to go 2 meters per second times 25 seconds. So to me that looks like I'll be 50 meters. And where will I be? Well, I'll be 50 meters. The easiest way to describe this would be downstream from the point at which I started. And if you think about it, that represents the distance that I've drifted downstream from my starting point. Okay? And so, now the third thing we might want to know is which way do we actually go? If I draw a reference marker on my picture here, well, the red line represents the way our boat actually went. Maybe we should try to figure out what that relative velocity actually was and what direction it was in. So now I'm going to go down here and redraw that triangle so we don't have to keep going back and forth. And we'll do question number 3. which will simply be, what is the relative velocity? Well, there's my paddling velocity, which was 4 meters per second. So I'll put the number on there. Here is my current, VC, which was 2 meters per second. And then we had the result, which goes from here to here. And I'll put in some little reference markers. It's always a good idea to put little reference markers at all of the spots on your, all the corners, just to give you some perspective. And those will come in handy later when we do more complicated questions. Okay, well, this is VR. So let's figure out VR. Well, what we do now is we just use all our triangle math. And because we know it's a right angle triangle, that will make our lives a little simpler. But it doesn't have to be. It could be a obtuse or whatever triangle that's not right, and we have to use sine law, cosine law, and so on. Right? You still with me there, guys? All right. So what we're going to do here is, I think, the easiest thing to do is Pythagorean Theorem. C squared equals A squared plus B squared. And so VR squared will be 4 squared plus 2 squared. So VR squared is equal to 16 plus 4. And so VR then would be the square root of 20, which is about 4.5-ish meters per second. But that's only the magnitude. What about the direction? For the direction, I might have to figure out an angle. So let's look at angle theta here. That would work, eh? North, theta degrees east. So let's figure it out. And to figure out that, we could use sine or cos or tan ratios, nice and simple. I'm going to choose tan because I know the 4 and the 2 are right. I might have made a mistake getting the VR, so I won't use that one. I'll use tan theta instead of sine or cos. And it would be opposite, which is 2, over adjacent, which is 4. So tan theta equals 1/2. And what do you get when you do the inverse tan of 1/2? Anybody? Everybody's tired today? Now it's about 27-ish degrees, 26.5-ish, 26.6, 27 degrees. So my answer for the relative velocity could be 4.5 meters per second at an angle of 27 degrees. Now I could do north 27 degrees east, but I didn't really know if that was north or south or east. Rivers can be in any direction. So I think the easiest way to do that would be 27 degrees downstream. 27 degrees towards downstream, which is the way the current flows, right? Upstream is against the current. So that's probably good enough. So what this means is if you paddle at 4 meters per second straight across a river, while a current tries to drift you downstream at 2 meters per second, someone on the shore would see a relative velocity, which is the sum of those two, which would make you appear to be moving along this red line at 4.5 meters per second, and it would be 27 degrees off of the black line. Okay, good. Now let's try and do another problem altogether. So let's just draw a line under that and do something completely different. I'm going to draw 2 pictures, but they're both the same picture. I just want to use 2 different triangles so they're not confusing. So here's going to be another river. In fact, it could be the same river, 100 meters across. And we're going to use our arrows. Here's where you're starting, right here. And this time you're going to swim across the river. Swimming is the same as being in a boat. Over here is a little building. And this building is called the quadruple B, which stands for Bob's Beef and Bacon Barbecue. So this is where you're headed. And we're in a bit of a hurry because whoever gets there first gets the bacon. Whoever gets there second has to settle for the beef. And we all know that beef is way better than bacon. No, I'm sorry, bacon is way better than beef, right? Yeah. steak all tastes the same, but pork chops don't taste like bacon, and that doesn't taste like ham, and the pig is a wonderful animal. So, you're going to swim on this river. Now, I'll give you a little current here. Here's a little current vector, VC, and I'll tell you down below that the current is going to be 2 meters per second. I'm also going to tell you that your speed of swimming, we'll call it VS for your swimming speed, is going to be 3 meters per second. And you can also run, so the speed of running is going to be 5 meters per second. Okay? And then over here I'm going to draw the very same picture because it's the same thing, except this picture is for your friend who's standing right beside you. There's the quadruple B. And your friend, of course, is thinking that they want the bacon and they want to stick you at the beef, so everything's the same, and they want to get there first. And your friend is exactly the same as you. Of course, the current is the same because it's the same river, and your friend has the same swimming speed as you do. Normally, you would be able to run a lot faster than you could swim, but for simplicity of numbers, we'll just pretend that you're an awesome swimmer, but a pretty crappy runner. So you're kind of the same, 3 and 5. Now here's what's different about your past. Here's your friend, right? We'll make your friend a girl so we can tell the difference there. Okay? You are going to swim straight towards Bob's, okay? Straight across the river. So this is how your swim will be on the picture. And of course, we've seen that if you do that, you would have to add the velocity of the current this way, tip to tail, and it would produce a result where you're actually going to end up going downstream like this. So that means you're going to actually get out of the water over here, and you're going to have to run back to Bob's, because you've drifted downstream. But your friend is thinking, I've got a better idea. Instead of heading straight to Bob's like this, she is going to point herself upstream at an angle, and it's going to be just the right angle so that this current vector right here will be just long enough to put her right at where Bob's is. Okay? Because I have to label this, I have to erase Bob's. Don't worry, he's still there, and there's plenty of beef. But not bacon. I'll just put Bob up here. There's the house. So that's our VC current. But notice how I've drawn it. I've had to draw it so that I needed the result to point straight. This has to be the result because she doesn't want to drift. She just wants to get there, hop out of the water, and not have to run anywhere. So her resultant is the path she wants to follow, straight across the river. But if you notice in both cases, this statement, VR equals VS plus VC is still true. This is VS. VS and VC are still tip to tail in both pictures. Right? So we're not violating our rule. Our rule is a resultant vector has to be the sum of the other two. Some students think that because this looks a little bit like Pythagorean Theorem, that the red resultant has to be the hypotenuse all the time. But that's not true. It can be any side of the triangle. What really matters is that the other two have to be tip to tail. That's the key.
Excuse interruption. At this time, I'm asking classes on the 3rd floor to proceed to the gymnasium for our